Hello students, so we're continuing on with our review of oscillation, waves, and sounds, and focusing now on waves. So let's get going. So wave was an organized, or is an organized disturbance, and it's got wave speed, and we talked about how a wave actually transmits energy overall, and the medium will go temporarily up and down, left and right, or something like that, but it really does not travel the medium, the water, the air, whatever it happens to be. And a wave transfers energy, does not transfer material or substance. We talked about a transverse wave versus a longitudinal wave, traveling waves, and what actually causes that wave, and it's the inner workings, the inner nature of the medium. In this case, with a rope, it's the tension between the particles, and you can look at a diagram and kind of think through what a particle right here is being pulled up by the particles on its left, and it's being pulled down to the right by the particles on its right, and so it's going to experience a net force, in this case up, and therefore it's going to accelerate upward, and that's how you get its motion. Wave on a string, that's a transverse wave. Sometimes you get a pulse. That pulse continues because of, like I said a minute ago, the internal dynamics of the medium. So if the wave's going this way, the question might be, which way is this particle going? And you just need to think about how is this being affected by the particle on its left and by the particle on its right. Sound waves are longitudinal waves, and they're formed by the compressions and rarefactions of the air molecules. The speed of sound, values that we use, 343 meters per second, and then the speed of light, 3 times 10 to the 8th meters per second. And I know this value right here is on your AP formula chart. If we graph waves, there's a snapshot snapshot graph, which shows just if you were taking a quick picture of what the medium would look like. Then a history graph, which was the graph of the wave at various times, and you just the history graph, I guess I would add, it's the graph, the history of one point on the whole wave. The snapshot's actually going to show you this point of the, let's say this is a string, this point of the string, this point, this point, this point, this point. The history graph is going to pick one point. You can see they've got x1 throughout, and showing what happens to that point right there. Well, first it goes up slowly, then he hits the peak, then he goes down slowly. So if you're looking at a snapshot graph, then the distance from peak to peak, since you're taking a snapshot, then that's the wavelength. If you're looking at a history graph, you're looking at one point, then from the time that it's at its highest till the time it's highest again, then that's the period. And a simple way of figuring out, are you looking from peak to peak, is that wavelength of period, just look at the x-axis. I mean, the period is measured in seconds, and so if your units here are seconds, then that's probably going to be the period. If your units are meters or feet or something like that, then, well, that's a distance, and so that would be the wavelength. So nice little easy way of identifying those two. We mentioned sine waves and the amplitude, and a lot of this stuff was covered in oscillatory motion. Then you had the wave formula, that the velocity is equal to lambda f, or the way that it's going to, you'll see it on the AP formula chart, that lambda, the wavelength, which is in meters, is equal to the wave speed, or the velocity of the wave, which is in meters per second, divided by the frequency, measured in hertz, or the base unit inverse seconds, 1/seconds. Sound and light waves, I already said sound waves are compressions and rarefactions where the pressure changes. Light and electromagnetic waves form the electromagnetic spectrum. Visible light is just a portion of that. Energy, just as we mentioned at the very beginning, a traveling wave transfers energy, and the power is the rate at which that wave transfers energy. If you have a lot of waves hitting, then that would affect the intensity. Intensity is power divided by the area. One way you can have more energy is just more amplitude. And also, if you're closer, you're going to experience greater intensity. So the intensity is the power divided by the area, and if that's a circle, then that, or sorry, a sphere rather, then that's going to be 4 pi r squared, surface area of a sphere. And the farther you get away, then obviously that power is going to diminish because it has more of a surface area for which it has to spread out. Loudness of a sound depends on the amplitude. The pitch depends on the frequency. Higher pitch is higher frequency. The decibel scale and the reasons why that was a logarithm scale based on the amazing range of the human ear, what sounds we can hear. The Doppler effect and shock waves, definitely expect to see something along these lines on that AP test, where if you have an object which is moving, then the apparent frequency can change. A person over here, if the object is moving closer to her, she will hear a higher frequency. Meanwhile, this guy over here, Pablo, is going to detect a lower frequency. Also, shock waves, where a particle is moving as near the speed of sound, or maybe a little bit faster, where it's actually it's going to be in this picture going faster than that, than the speed of sound, and the wave fronts here all sort of pile up, and an observer here would hear the sound sort of piled up on top of each other and hear a very, very loud, loud roar, sort of thunderous sound, which is what we call the sonic boom. All right, that's it for waves. Stay tuned as we talk about superposition and sound.